Hello everyone, this is Professor Ma and this is the short lectures on the sections on transformation of graphs. Uh, in the last few sections when we went through the basic graphs of algebraic functions, polynomials and rational formulas. Okay, specifically the relationship between the formulas and the picture, the graphs. In this one, we're a little bit more abstract. That is, we're going to again study the relationship between the algebra and the pictures, except in the general settings of the function notations. That is, if I have using the function notation, if I change the function notation in abstract settings, numbers if I change a little bit, what's the effect on its graph in general? Okay, so here we go. Lot of the reason we do this is because that allows us to visualize some graphs that are made up of simple some basic graphs, and these particular pictures will give you some of the basic graphs. And somebody made it up um, uh, in the past, so I leave this to you. And this is pictures, just by playing around, and we can make strange pictures like these. Okay, which is related to the topic we're going to talk about. Okay, so let's start out with this in let's for instance in here in the PowerPoints, and we have a tool which allows you to draw graphs, and which is you can shape curves and change colors and do all type of stuff and stretch and expand it. So in a basic software manipulation tools, you have all these very basic capabilities. Okay, I'm sure you all used it before. You can take a picture, you stretch it on screen. I can move the pictures on the screen somewhere else, left and right or up and down. Okay, and I can flip it, reflect it if you like. Okay. And all these steps are related to if I know the original formulas, y to f of x, the original shapes, that all these transformations can be obtained by doing a simple things to the original formula. Okay, so let's start off with the basic settings. Okay, the important part over here, the basic important thing ingredient here is that I have a curve given by some formula y equals f of x, and I have a point x over here. And that associated with x is a point on the curve, x, y. Y, of course, is the another name for the f of x. Okay, that is always the interchangeable, depending on whichever things is easier, more convenient for me to realize the context. That's it. Okay. And in particular, in this case, y is the y coordinate, and so in other words, that's the height of the point. Okay, so that is very important. Okay, and so let's translate now various operations about this changing this curve into algebra. So the first one, vertical translations. Okay, so suppose I want to move the point P up to 3 units higher. So now it's up here, and all I have to do is add +3 to the y coordinate. And if I do this to every point f of x, then the entire curve will be lifted up 3 units. So the pictures for y of the function f of x +3 is going to be the original functions the curve graph up by 3. If I is minus 3, it goes down by 3. Okay, so this is the first observation. So if I were to add or subtract a number, assuming it's positive here, and then plus c goes up, minus c goes down to the y coordinates. Okay, you have to keep track of which coordinates you're adding, subtracting number. It's very important because later on we'll do the other ones. Okay, so the second one, what happens if I want to multiply the y coordinate by a constant? Let's say now I have a function y equals 3 of f of x. So well, if here's original height f of x, now I want to plot a new point, the same x, except this is going to be 3 times f of x, 3 times y, meaning I want to triple the height. Okay, if I do this to every point, then everybody will be, height will be tripled, and the lowest point, the height will be tripled, and notice 0, 3 times 0, 0, so they don't move. So in this case, if I were to do tripling the height of every point, I wind up stretching the original curve 3 times as high. Okay, and at the 0 place, they don't move, they fix. So this is the effect of multiplying a number to 1. This is k times f of x, and here's a summary of it. Okay. Oh, by the way, if I divide it by 3, then I will be compressing the curve to 1/3 of its original height at every location. Okay. And this is what you do. Sometimes you see on the TV screen, when TV goes out, the old ones go, they compress, or this is the changing these vertical compression ratios, if you like. Okay. And here's a summary for it. Okay. And so you can read through. If you multiply by a number more than 1, you're stretching it. If you multiply by a number less than 1, you are compressing it on the right hand side. Okay. So this is the what we do if I change the another ones. If I were to multiply by -1. If I multiply by minus numbers, and then the y coordinate will reflect down to -y. So positive 1 on top will be flipped down to -1 down the bottom. So the entire curve will be, if you like, flipped. Okay, twist, flip along the x-axis. Okay, reflections, if you like, vertical reflections. Okay, and so -2 f of x will be after you reflect it, you double the height. Okay. And this pretty much gives us the what happens if I take a formula, multiply the formula by some number, and after multiply, and maybe I subtract some number outside. That's plus c. So okay, so we are taking care of that. But we haven't. Now let's talk about what happens if I actually go, change x a little bit. Actually, this has to do with horizontal operations of the curve. Okay. Oh, this is examples that say, and so what you need to do, g of x, basically you need to take f of x, you need to stretch it twice as, reflect it if you like, change track of what this point goes to, and this point goes to, and this point, and then you need to double the height, -2, and basically these questions ask you to track the endpoints, okay, and to see what the function g of x look like. One thing about translating the graphs, these type of operations, you basically get some kind of distorted versions of the original shape. Maybe it's really flattens out, maybe it turns upside down, but it doesn't change the idea. It's a V shape with arms, attached to it. Okay, it's not going to change into that. That is, goes like a V shape, then goes back down, and it doesn't do those type of translations. Okay? So I'll let you go through and keep track of each point and see where each point translate into the locations, and then we plot it, and this is the end result. Okay. Now let's do horizontal translation. Now let's say what happens if I were to change the x. Okay, and so let's say we replace x by x plus 1. What do we mean? What do we mean by that? What do we mean by that is, suppose y. I mean, I can actually give you an example. Suppose I have to form a formula y is 2x and x plus 3. Let's say, okay, that's f of x. Then I can replace x by x plus 1, and that would be all the x will be replaced by x plus 1, x plus 1 plus 3, and then clean the versions to x plus 2, expanded version if you like, x plus 4. Okay, so this will be f of x plus 1. So this is f of x. This is f of x plus 1. It doesn't quite look like anything related to original f of x, of course, because I cleaned it up. I mean, these, of course, I'm going to call g of x. Okay. So this is an example if you keep in mind. Okay. But this is basically what went on, but the specific formula is not important. Just remember that basically this, after plugging x plus 1, I get a new formula. And the point over here is I want to plot the new formula. How should I plot it? Okay, here is the picture of f of x. And here I do want to warn a lot of people. It will say, oh, x is changed into x plus 1, so all I have to do is take this piece of snake or curve, move it plus 1. No, actually, we move it the other way, and that a lot of time bothered a lot of students. So the way to think about it is, okay, let's call g of x to be the formula after you plug x plus 1 into it. And I want to plot g of x, right? And here's point x. And of course, if I want to plot g of x, then the point for related to g of x will be somewhere over here. I don't know where's g of x, right? And how high do I plot g of x? I don't know. And here is what instruction tells you in the definition, how g of x is defined. That's the important point. Okay, I want to emphasize this because a lot of these horizontal things concerning plugging in something to change the x is related to how we view the graph will be changed. Is through this angle. You will see why the things move to the left. The instruction says to find out what g of x is, you go to f of x plus 1. In other words, you go from x plus to x plus 1 first, which to the right, and you look up and you see what f is. that of course is the f of x plus 1, right? You take that measurement, bring it back, and that will be the same as the g of x. In other words, that point is going to be brought back, and that's your point x, g of x. Okay? And you do that to every point x along the x-axis. You go to one unit to the right, you look where f is, bring that, slide that back to where your x is. That's your g. Okay. And here's another point u. You go to u plus 1, you bring that back. And if you do that to every point, you shift the graph to the left by 1. Okay, that's what the entire, how the relationship between the algebra and the pictures. Okay. So, if you plus the number, you move to the left, f of plus c. Okay. If you minus a number, x minus c, then you move the curve to the right. The result is the curve just 2 units to the right. Let me, whichever way we use a similar analysis. What happens if I were to multiply the x by a constant, let's say 2? Okay. And so if I have a point g of x, okay, how do you find what should I plot? And here's g of x. Where should I plot g of x? You know, where g of x is what? Well, it says you g of x, you double the distance to 2x, and you look up at f, you bring the f back. Okay. So that's the instructions for plotting g of x. You do that to every point. Okay. You bring them halfway, if you like, to 0. I mean, from between 0 and x. And what happened in f of 2 of x? If you plug in 2 of x, it compressed the curve, original curve this much, and now you pressed to the halfway. Okay, that's the horizontal, you know, on the word processing software. That's the horizontal squash, if you want. Okay. And this is similarly reasoning. This gives you the relationship between f of x and f of minus x. F of x and minus f of minus x are the horizontal reflections of each other. Okay. So these are all the basic effect when we change the formulas f of x a little bit. Okay. This is a summary of them. Okay. These just when we this particular paragraph says this. When you have a for instance, if f of x is defined over 0 and 1, here's roughly 1. Then the formula you're going to make f of 2x, which is of course a new formula, which is g of x. Okay, g of x will be defined over twice as much. Okay, we actually go from 0 to 2. Okay, it will double the domain. Sorry, half, because I'm squashed it. It's divided by 2. My mistake. Okay. Goes exactly the opposite. And then the series of compressions, horizontal compressions. What else? What are some other things we do to graph? Absolute value. When we put absolute value around the functions y, and we change all the negative y's, and then in the absolute value version, it says, oh no, and they have to change the positive. Effectively, you change these points up, reflect up to there. So when you finish, you get these V shapes. And so these are general. Then if I slap absolute value around the formula, it doesn't affect the part that sticks out on top, where the y's are positive, but the negative parts you have to, like in this parabola, you have to take the negative part and flip it over. When you finish flipping over, it looks like this. Okay, so absolute value that after I flip over, I subtract 1, I will take this and drop the whole curve down by 1. That would be the formula for these particular strange shapes. And if I were to do what else I do, that nice stretch it, make it sharper. Okay. And so this is a series of change in graphs when we play around with these absolute value calculations. Even and odd functions. Okay. On odd functions is when we put into f of x, this minus sign can be pulled out. Okay. Even function is where the function where I pull minus into plug in minus x, I get the same as original f of x. Okay. Here's the definition of odd functions, but f minus of minus sign can be pulled out f of x. Okay, not every function is even or odd. Okay? Most are not. That only a few, like for instance, here's an even functions. Why? Because if I'm putting minus x and putting plus x, I get exactly the same formula. Okay, because the even powers makes minus sign disappear. So in other words, the graph is going to be symmetric left and right. Putting minus x plus x, the same y comes out. So the graph is symmetric left and right, horizontally. Then there's a type where if you put in minus x, then the y becomes negative. And these the relationships I'm plotting is the 2 points you plotted x and minus x, is they are the reflections across the origin. Okay, so here's a picture. Okay, one's x f of x, and the other one is minus x minus f of x. So the functions are if it satisfies these conditions. In this case, the R functions, it is symmetric. The picture is symmetric across the origin diagonally. Okay, like that. So the top is pictures of even function. The bottom is a picture of odd functions. Okay, and they all center around 0, of course. It have to be 0, 0. Okay, and except for the even function. I can have a constant terms. Now, where did the name come from? Well, if a polynomial has every power odd power, then it's an odd function. Okay, because I plug in minus x, the minus sign can be extracted. Okay. And here are the basic fact about even function and odd functions. Okay. That's it. So these are things to notice and do the homework and have a good day. Bye-bye.